Since the earliest days of the Industrial Revolution, steam was used to power machinery and as a medium for distributing heat. Today, the excellent heat transfer properties of steam, as well as the ease with which it can be distributed and controlled, have led to its wide use throughout the world. In the U.S., the use of steam in industrial processing is so widespread that nearly half of the industrial fuel consumption goes to the generation of steam. A modern steam system is designed to transport energy from a central location, the boiler, to a variety of locations in the plant. Low energy, maintenance, and operational costs in your system can be achieved by proper design and maintenance, which promotes system efficiency. Steam systems consist of four basic components: the boiler, the distribution piping, the heat exchange or process equipment, and the condensate return. The boiler must be sized to generate the amount of steam required for the process or heating load, or both. Many steam system troubles can be traced to an undersized boiler. If the initial sizing was inadequate or additional loads were later added, the demands for steam could exceed the boiler's capacity. Such undersizing will result in inadequate steam pressure and consequently lowered temperature. Waterside care also affects boiler operation. Improper water treatment is detrimental to both the condition of the boiler and the quality of the steam produced. Improper care can lead to scale formation, pitting, and corrosion, greatly shortening the life of the boiler. Have your boiler inspected at least once a year. If problems are evident, consult a competent feedwater treatment company. Steam mains must be correctly sized to ensure efficient operation and to minimize maintenance costs. The size of the steam main piping is determined by the allowable pressure drop and velocity for a specific pressure. As velocity increases, so do noise levels, erosion potential, and the amount of pressure drop. The greatest pressure drop in the distribution system should not exceed 20% of the maximum boiler pressure, radiation and friction losses included. Remember, pressure drop is energy loss. Although the initial cost may be higher, oversizing steam mains to reduce velocities and pressure drops can help minimize future trouble and expense in your plant's operation. Steam mains must be insulated to minimize wasteful heat loss. But even in well-insulated steam mains, there will be some condensing taking place. Drip legs and drip traps must be installed to automatically drain the mains of this condensate. Drip legs divert the condensate from the fast-moving steam in the mains. They also provide a pressure differential during startup, enabling the trap to discharge the condensate to a gravity return. Drip legs should be the same size as the steam mains on pipe sizes up to 4 inches in diameter. Above 4 inches, they should be at least 1/2 the size of the main, but never less than 4 inches. The depth should be at least 1 1/2 times the diameter of the main, but never less than 10 inches. Steam mains should be dripped every 300 to 500 feet. Also, install drip traps immediately ahead of risers, expansion loops, pressure-reducing valves and temperature regulators, at the end of steam mains, and on long runs of branch lines. Select a trap based on the calculated condensate load, not on the pipe connection size. Other considerations in trap selection are normal steam pressure, fluctuations in pressure, ambient temperatures, and the likelihood of dirt in the system. Use a 2-to-1 safety factor for drip traps between the boiler and the end of the main. Use a 3-to-1 safety factor for the trap at the end of the main, and for traps ahead of shutoff valves, pressure-reducing valves, and temperature control valves. Branch piping or runouts from the steam main should always be taken from the top of the main. Runouts of less than 10 feet can be pitched up from the main at 1/2 inch per foot and do not require a drip trap ahead of a PRV or control valve. If the runout is more than 10 feet, it should be pitched down from the main with a strainer and drip trap installed immediately ahead of an automatic control valve or PRV. One practical recommendation is to install the drip trap on the blowdown connection of the strainer ahead of the valve. This arrangement will automatically blow down the strainer while providing the necessary drainage of condensate. It also prevents condensate from accumulating in the strainer. Condensate standing in the strainer body reduces the total effective area of the strainer screen and can lead to the damaging effects of water hammer. Inverted bucket traps work best for this type of service due to their ability to handle dirt. Efficient use of steam with heat exchange and process equipment requires proper trapping. The job of the steam trap is to get the condensate and non-condensable gases out of the steam space as fast as they accumulate. The condensate must be removed quickly or it will reduce the performance or heat transfer ability of the equipment. Non-condensable gases must also be removed from the steam space by the trap, and it is important that they be removed at or near saturation temperature of the steam. Oxygen and carbon dioxide are released in the boiler when steam is produced and travel through the distribution piping. When CO2 combines with condensate that has cooled below the saturation temperature of the steam, carbonic acid will form. This acid is extremely corrosive and will eventually eat through the heat exchanger cores and piping. Oxygen in the system furthers this destructive force by causing oxidation. Proper selection of trap type and size is based on the condensate load, steam supply pressure, pressure modulation, return line back pressure, and specific application requirements. Do not select traps on the basis of the equipment's condensate outlet size. Regardless of the type of trap selected, install a drip leg, a T, and a 6-inch dirt leg from the condensate outlet of the process or heat exchange equipment. The drip and dirt legs should be the same size as the equipment's condensate outlet. From the side of the T, install a strainer to protect the trap from dirt. When using mechanical traps, the drip leg should be 10 to 12 inches long. When the trap's valve is closed, the only force that moves the condensate to the trap is gravity and a slight differential pressure created by collapsing steam, so the trap should be located as close to the equipment as is practical. Thermostatic and thermodynamic traps should have a longer drip or cooling leg, placing the trap further from the equipment than is recommended for mechanical traps. The reason for this is that thermostatic and thermodynamic traps back up condensate each time the valve closes. Thus, a longer horizontal or vertical drip leg is needed to prevent condensate from backing up into the heat exchanger. Each piece of heat exchange equipment must have its own steam trap. Group trapping, the removal of condensate from several heat exchangers through a single trap, can cause backflow of condensate and air into the heat exchanger with the greatest pressure drop. Even with a check valve to prevent backflow through the trap, condensate can accumulate because steam is still condensing in the heat exchanger. The results of group trapping can be loss of efficiency, water hammer, corrosion, and damage from freezing. To eliminate air from steam in processes using chamber-type heat exchangers, use thermostatic air vents. Air is an excellent insulator and is present in steam systems at startup. Air moves with the steam to heat transfer surfaces where the steam condenses, leaving the air behind. This air collects, insulating the heat transfer surfaces from the steam. Under these conditions, as little as 0.5% by volume of air can reduce heat transfer efficiency by as much as 50%. In addition, an air-steam mixture has a lower temperature than pure steam. Install thermostatic air vents at the top of the heat exchanger's steam space and as far from the steam inlet as possible. Air vents are typically used on jacketed kettles, retorts, vulcanizers, jacketed sterilizers, and most batch process equipment. A vacuum breaker is needed on a heat exchanger under modulating control, which is used to heat water, air, or product to less than 212 degrees Fahrenheit. Under these circumstances, when the control valve closes, steam in the heat exchanger condenses, creating a vacuum. If the process calls for low-pressure modulated control, A small amount of steam will enter the heat exchanger, but will not be sufficient to break the vacuum. This steam condenses, adding to the condensate accumulation. If there is then a sudden demand for heat, hot steam in contact with the cooler condensate causes water hammer. The collected condensate can also result in carbonic acid corrosion in the heat exchanger and may freeze under certain conditions, damaging the heat exchanger. All of these problems can be eliminated by the quick evacuation of the condensate. A vacuum breaker will allow the necessary drainage, provided there is no back pressure in the return. Since a vacuum can exist in the heat exchanger and discharge piping while steam is entering the heat exchanger at a slight pressure, install the vacuum breaker on the discharge side of the heat exchanger ahead of the trap. A vacuum breaker on the supply side would not open under these conditions. To simplify the installation, F&T traps with integral vacuum breakers can be used. Ideally, condensate should flow from the steam trap by gravity to a receiver. Such an arrangement is not always practical, however. In some applications, the only space available for return lines is overhead, so condensate must be elevated from the trap. The force to elevate condensate is provided by the differential pressure across the trap. Since each 2 feet of lift reduces this differential pressure by 1 pound, be sure there is adequate pressure both to elevate the condensate and to maintain adequate trap capacity. When elevating condensate, use a check valve, either immediately downstream of the trap or integral to the trap. This prevents backflow of condensate into the heat exchanger when the control valve closes. Heat exchangers under modulated steam supply may not always have sufficient pressure to lift condensate to overhead returns. For these applications, a safety drain trap is required. A safety drain is an auxiliary trap with its inlet above the primary trap inlet. If there is insufficient pressure, the condensate backs up, rising until it enters the safety trap, where it is wasted to an open drain. When there is adequate pressure to elevate the condensate, the safety trap is bypassed. Return lines must be adequately sized. Hot condensate discharging into the lower pressure of the return line produces flash steam. Return lines must be sized to handle this mixture of condensate and steam. If return lines are too small, high back pressures and excessive velocities will result. Excessive back pressure affects the operation of thermodynamic traps and reduces the differential pressure across all types of traps, thus reducing their capacity. High velocities in return lines increase the likelihood of differential shock and erosion. Keep discharge lines as short and straight as is practical. Assuming the trap to be properly sized for the application, use pipe the same size as the trap connection. If pressures to the trap are very low, increase the discharge line 1 pipe size. The return main must be sloped in the direction of flow at least 1/4 inch per 10 feet. Trap discharge lines must enter return lines at the top. Avoid discharging low and high pressure returns into the same return main. High pressure lines release high temperature condensate. If this condensate combines with lower temperature, low pressure trap discharges, water hammer can occur. When discharge lines must dip, such as passing under a doorway, avoid air binding by piping a smaller parallel line over the doorway. Condensate receivers and their vents must be properly sized to minimize back pressure in the system. The vent should be the same size or 1 size larger than the condensate line into the receiver. Condensate pumps must have the correct NPSH to ensure the efficient return of hot condensate to the boiler. Freeze-prone environments present their own special set of problems. A thorough discussion of these problems and recommended solutions is contained in the Armstrong video program, Guidelines for Freeze Prevention. To view this informative program, talk to your Armstrong representative. The Armstrong Manual M101, titled Steam Conservation Guidelines for Condensate Drainage, is an extremely valuable reference book. It contains the guidelines outlined in this program and many others as well. Your facility's steam system is one of your most important tools. it makes sense to see that it operates as efficiently as possible. By following the guidelines we've outlined, you can hold energy, maintenance, and operational costs to a minimum and enjoy the benefits of an efficient, dependable system.